The situation is we have a charge at the vertex. Here is the charge Q at the vertex of a cone. Here is the cone, and we are trying to find the total amount of flux passing through the cone. Okay, so this situation actually needs the visualization. uh, Visualization is very important here. First of all, grab this fact that total flux passing through this base, total flux passing through the base of this cone, that is this shaded area, will be equal to the flux passing through the part of the sphere which is having the center as the vertex of the cone and radius as the slant height. Let us draw a better picture. Say this is your sphere, and now here is the here is the center, and this is the slant heights, right? Can you visualize the situation? And well, this is the base of the cone. So the total number of field lines which originate from this Q will surely pass through the base of this cone and then pass through this blue portion. This is this AB part of the sphere, right? So how? So if we will basically calculate the flux passing through this AB part of the sphere, and that will be our answer. So how to calculate that? Now we know that total flux passing through the whole surface of the sphere is Q by epsilon naught. This is from Gauss law. So total flux passing through whole surface is pi equal to Q by epsilon naught. Therefore, the flux passing through the base of the surface is this flux, the phi flux is passing through surface area what? 4 pi capital R squared, where R is the slant height of the cone or radius of the circle. So therefore, per unit area, the flux passing is basically Q by 4 pi epsilon naught times R square. So the flux passing through this AVA area is basically S dashed, right? This is basically S dashed. So if we can find the area of A dashed, we will substitute the value of S dashed here, and we can find the value of phi dashed. So how to calculate that? Say sorry is the height of the cone, okay, and say this angle is theta, okay. Now to find the area of the part of the sphere AB, that is basically called lune, the area of the lune, to find the area of the lune, what we are going to do is we will take an elemental area. What is that elemental area? Try to, this time you need the visualization. This is the elemental area. So the shape of the elemental area, please see this figure for yourself. Again, I know this part is a bit complicated. It is like this one. Check, please check clearly. uh, okay, this is the height, which should be in basically green line, whatever. And this is R, and this shaded area is our elemental area. We will have different such elementals area, like I am drawing another. See, this is another elemental area. There is another elemental area. There is another elemental area, and all these elemental area will gradually complete the lune. Okay, and if this angle is alpha, let's take another color. Okay, now let's get back to, this is alpha, right? So where is alpha here? In this picture, alpha is, this picture alpha is, mm, this is alpha, and basically this is actually, this is alpha, and the pink line, I mean alpha is almost from the midpoint of the elemental area, and here this angle is this very small angle, that is basically increment of alpha, which is basically d alpha. Okay, so what is the area of the shaded part, that is area of the elemental part? The area of the elemental part, that is ds. Ds is basically what, if the this radius is smaller, then the shaded part is 2 pi r, that is perimeter of the pink circle, times thickness of the mm, elemental area, right? So this thickness, check it, this thickness is basically what, this is r d alpha, right? So this angle is d alpha, so this is r d alpha, this thickness is r d alpha. So ds is basically 2 pi r times r d alpha. So to get s dashed, we need to integrate this one. What is the limit? Check this figure out. The bigger circle where the whole sphere is drawn, the alpha starts from here, alpha equal to 0, and at the end alpha equal to theta. So the limit of integration will be, so s dashed will be equal to integration 2 pi smaller capital R d alpha, where the limit runs from 0 to theta, right? Now small r is a variable. You can see if we take different elemental area, like if that we take elemental area here, I'm not drawing that, that will make the figure clumsy. But if we draw it here, small r would have varied, but capital R is a constant. Small r and d alpha would have varied. So what is the relation between small r and alpha? That is from this figure. Check this figure. This is alpha. So small r is equal to basically capital R sine alpha. So this integration is basically 0 to theta. This is 2 pi. Small r is capital R sine alpha. So this is 2 pi capital R square sine alpha d alpha, right? So if we do the integration 2 pi r square will be out of the integration, and integration sine alpha d alpha is basically cos alpha. So putting the limit, uh, this is minus cos alpha d alpha. So this is basically cos theta minus 1, which calculation. So our is dashed, the value of is dashed is basically, 2 pi r squared 1 minus cos theta. And if we put it here, what we will get? 2 pi r square will get cancelled. So the phi dashed, that is flux passing through the lune or flux passing through the base of the cone, will be q by 2 pi will get cancelled. 2 pi r square, 4 pi r square, pi will be cancelled. So q by 2 epsilon naught 1 minus cos theta. 1 minus cos theta. Where what is theta? That should be clearly noted. Theta is the semi-vertical angle of the cone. Theta is the semi-vertical angle of the cone. Okay.